Alright, looking at number 3 here. Number 3 proposes the to find the expansion of e to the let's go with yellow. E to the 3x times the square root of 1 plus x. Again, you have a lot of choices. Either you can find the polynomial expansion for that and find the polynomial expansion for that and multiply them, sort of like a big super foiling problem. We did that earlier, and here now I can show you something different, just so I can show you a lot of different ideas. You could also just do it the very same way we did it in class, just back to basics, where you use this excellent formula to compute the expansion. So I've gotten a little calculator here that will help us. So I put in there the function f of x is equal to, this is a fancy way of saying e to the 3x plus times the square root of that. That's the function, right? And my point where I'm calculating is, according to the problem here, is x, I know you can barely see it, is x equals 0. That's where we're starting our expansion. And so the first coefficient of the construction of the polynomial would be just a function evaluated at 0. So I put f of c, because c is equal to 0. And then that's my constant term. My linear coefficient will be the first derivative, and you just evaluated x equals c. The second one will be the second derivative divided by 2 factorial. And then once you do that, you replace x with your constant. This part right here means replace my x with a constant. The third one is the third derivative divided by 3 factorial. That's exactly this formula being expressed. This is Mathematica syntax, by the way, but you can use any calculator you want. Anyways, you do that, and it will be a little arduous problem, but you can do it, and you get that the first constant is 1, the second one is 7/2, and the next one is 47, whatever. And so you get the expansion looks roughly like this. This is going back to the very basics, using no fancy trick whatsoever. And that should be enough to see which one of these might be the problem. So according to our calculation, the first coefficient should have been a 1. So they've got to start off with a 1. That rules out C, as C appears to be starting at 2. And that leaves these ones. The second coefficient should be 7/2. That rules out this one. That's pushing you towards D. The third one should be 47/8. And this is nothing fancy. You're just calculating, plugging things into this formula, finding out the coefficients, and there you go. You're done. It's clearly a D, I believe. And so that gets it done. I should maybe say other things about it. And the other way to do it would be, again, using the famous formula. You have e to the x. We have an expansion for e to the x. E to the x is 1 plus blah. Whoa. 1 plus blah. That would be e to the sorry, I'm spacing out. So e to the x is equal to 1 plus x squared. So therefore e to the 3x would be 1 plus 3x plus 3x squared over 2 factorial plus 3x to the third over 3 factorial plus 3x to the fourth over 4 factorial, and so on and so forth. That's that one. And then to do this one, that one would be, well, we have excellent formulas for that one. If you don't want to do it by hand, we have already done it. It's this binomial expansion. I don't think you can see it on the screen. Let me move it forward here. I think you can see it now. This one right here. It's the expansion. It tells you how to expand 1 plus x somehow. And it tells you that the expansion would be 1 plus wait a minute, where's my p? Whoa, what? P should be 1/2, because this is 1 plus x to the 1/2, so that's your p. So this would be 1 plus 1/2, choose 1, x plus 1/2, choose 2, x squared plus 1/2, choose 3, x to the 3, and so on and so forth. And so you've got yourself you've got the expansion for that, and you got the expansion for that, and now you just multiply it out. And as easy as it sounds, that's all you got to do. Just kidding, it's kind of long. So, but you can do it. You can first multiply out the ones, and so the 1 would be 1 plus 1/2, choose 1, x plus 1/2, choose 2, x squared plus 1/2 choose 3x to the 3 plus so on and so forth. For the 3x, you'd go, okay, that's 3x times 1. Now I'm going to do 3x times this one right here. That would give you, I'll just do the coefficients separately, 3 times 1/2 choose 1, and then I have x squared. That's these two multiplied together. These two multiplied give you that. I'm just distributing this, and so 3x times that would give you 3 times 1/2 choose 2, and that would give you x to the third, and so on and so forth. For the next one, we'd have 3 square x square over 2 factorial times 1, perfect, plus the same thing but with that 3x square over 2 factorial times 1/2 choose 2 times x. That would give you a total of x to the third, and so on and so forth. This already might be enough for us to figure it out. So it'd be 1 plus that's 1/2 choose 1 plus 3 times x plus 1/2 choose 2 plus 3 times 1/2 choose 1 times x squared plus 3 squared over 2 factorial times x squared, and so on and so forth. So now you just have to compute this and see which one it matches. But already with the work we've done, well, I can see that okay, if it doesn't start off with 1, it rules that one out. I have to figure this out, and I can probably rule some of these out. By the way, what's 1/2 plus 3? 1/2 choose 1. Well, you have to think about that for a second. That comes from combinatorics. It's kind of a story in and of itself, but 1/2 choose 1 means 1/2 times divided by 1 factorial. That one's kind of silly. It doesn't show you the pattern. 1/2 choose 2 is equal to 1/2 times 1/2 minus 1 all over 2 factorial, right? And so on and so forth. 1/2 choose 3 would be equal to 1/2 times 1/2 minus 1 times 1/2 minus 2 all over 3 factorial, and so on and so forth. That's how you compute these coefficients. You can compute them, and then you'd see that again D is correct. That gives you a different point of view. Just that's already 2 tools. Multiply out the big polynomials. You think this is tedious? You haven't seen nothing. Sometimes we divide actually these long polynomials one by one, infinitely long polynomials. It's fun stuff. Anyways, this gives you one way to do it. I kind of prefer the other way, where we actually use the the old school way, which is just finding the coefficients one by one. That's kind of nice in this case too. That's what we did earlier. Alright, that's number 3. Maybe we should go on to number 4 here. 4 is talking about the accuracy and whatnot. The accuracy, what it's trying to do is have you, here, let me try to explain that. What it's trying to have you do is the fact that, let me say something about 4. 4 is interesting, and a little bit interesting. The fact that if you try to do this sine of the square root of x and dx, this seems to be a very difficult polynomial. Nearly, maybe it's not, you can't do it using normal regular elementary functions. Actually, it takes a lot of pain of extra money to do that one. So what it proposes is, hey, why don't you find a polynomial expansion for this, exchange this for a polynomial, and then do the integral. So we will exchange the polynomial. I'm looking at my famous exchange rate here for functions and polynomials. This one is the sine. Shoot, I know you can't see it. There. It's because I was trying to save room for me to write. So here's this famous sine polynomial. It looks like this. So sine of blah is equal to blah minus blah to the 3 over 3 factorial plus blah to the 5 over 5 factorial minus blah to the 7 over 7 factorial, and so on and so forth. So therefore, sine of x to the 1/2, well, that would be equal to x to the 1/2 minus x to the 3/2 over 2 factorial plus x to the 5/2 over 5 factorial minus x to the 7/2 over 7 factorial, and so on and so forth. So then integrating this is not so bad now. Integrate that, well, actually that side is still nearly impossible. This side is very doable with respect to x, evaluating from 0.3 to 0.7, from 0.3 to 0.7. So now it talks about some accuracy for decimal places. That tells you that it's not exactly, this is equal if you go all the way to infinity, but if you stop somewhere, it'll only be approximate. And so you shouldn't stop anywhere. Make sure that you get enough so that you get a good accuracy there. And but unfortunately, this problem should have appeared in the next one, where we talk about error control. But alright, it went here. You can still do it. Just do this out enough to where you get accurate answers. So you should try it up to x to the 7th, right? And see what you get. And if you don't get one of these, you should try x to the 8th. And at one point or another, the numbers will stop changing. And so, let me give you an example of that.